Welcome to this fourth video in a series on counting complex arrangements. Previously, we've learned how to count the number of subsets of a finite set and the number of bit strings with length n, and the more complex situations of k-element subsets of an n-element set and n-bit strings with weight k. At the end of the last video, we teased a connection between these last two sets that we're going to explore now. So in this video, we're going to revisit an earlier idea that if I want to count two collections of objects, and I know how to count one of those collections, I can count the other by setting up a bijection between the two sets that I'm counting. In this video, we're going to build a bijection between the collection of k-element subsets of an n-element set and the collection of n-bit strings with weight k. Since these are both finite sets, this will show they have the exact same number of elements, so the count of one set equals the count of the other. And more importantly, all the methods and relationships we use to count one can be used to count the other. We already did this in a special case earlier when we were counting bit strings and subsets. We said that we can form a subset of a finite set by voting for it using a ballot, and then notice that every ballot is just really a string of bits in disguise. That mapping of ballots onto bit strings was a bijection, so the number of subsets of an n-element set and the number of n-bit strings was the same, namely 2 to the nth power. So let's do something similar now. We're going to build a bijection from the set of k-element subsets of an n-element set to the set of n-bit strings with weight k. We never really came up with a formula for the size of the first set, just a method for counting it that involved doing an incorrect count first and then dividing off by an error factor to correct it. But we do have a number for the second set, namely bnk, which we can get by repeated application of a recurrence relation. Once we have this bijection, we can conclude that bnk also counts the first collection. So here is the mapping. We start with a main set that has n elements, which I'm going to label A1 through AN. Take a k-element subset, which is some selection of k elements from this n-element set. We're going to turn this into a bit string as follows. So first of all, set up an n-bit string by putting n blanks out. Now look at the main set that has n elements and loop through each of those elements. If AI is in the subset that we have, then we put a 1 for the bit in position I. Otherwise, we put a 0 and then return the bit string. Notice that this bit string has n bits and it has weight k because the process above puts exactly k 1 bits in the string. One bit for every element that was in my k-element subset that I started with. Here's an example of the inputs on the left and the outputs on the right of this process in the case where we are looking at 3-element subsets of a 5-element set. In the second line, it shows that if we take the same set but written in a different order, it produces the same output, which is what a function should do. This isn't a collision because those two sets are not different. Instead, this is illustrating that the mapping is actually a well-defined function. So let's see why this mapping is a bijective function. We've already argued that this mapping is actually a function when I give it one input, which is a k-element subset of a main set with n things in it. It sends it to exactly one bit string. It does not split it and send it into two different things, even if the subset can be written in two different ways. So to show that a function is a bijection, I need to show that it is injective, or one-to-one, and surjective, or onto. Let's start with injective. So to show that a function is injective, any function whatsoever, I need to start with two different inputs and show that I get two different outputs. The inputs to this function are k-element subsets. So let's take two of those, call them S1 and S2, and let's make sure that they are different. So that means that one of those two sets has an element that doesn't belong to the other one. Just without any loss of generality, let's say that S1 is the different one. It has an element X that doesn't belong to S2. So when I'm forming the bit string that corresponds to S1, I'm going to loop through all n elements of the main set and put a 1 if I encounter an element of S1 and a 0 otherwise in a bit string. So the bit string corresponding to S1 has a 1 bit in whatever position it corresponds to X. But when I make the bit string for S2, that same position is going to have a 0 in it because X doesn't belong to S2. So I'm going to end up with two different bit strings if I start with two different subsets. And that makes the mapping an injection, no collisions. To show that this mapping is a surjection, or onto, I'm supposed to start with a point in the codomain of this function and then work backwards to find an element in the domain that maps onto it. That means I need to start with an n-bit string that has weight k and construct or reconstruct a subset that maps onto it. So let's start with an n-bit string with weight k. So I have n bits, and k of those bits are 1. Can I build the k element subset that maps onto it? Well, I certainly can, because each of those n bits corresponds to a point in the main set. And so when I encounter a 1, that means I'm going to create a subset that includes that element, that whose position has a 1 in it. There are k of those positions, and so I'm going to have k elements in my subset. Just to give a concrete example, if I'm looking at a 5-element set and looking at 3-element subsets, and if I started with the 5-bit string 01101 that has weight 3, that would correspond to the subset BCE if I'm thinking of my main set as A, B, C, D, E. The ones tell me which elements of the main set to include in my subset. So since I can start with an n-bit string of weight k and build a subset that maps onto it every single time, that means that this mapping is a surjection. So that makes it a bijection. So what this proves is that the collection of k-element subsets of an n-element set and the collection of n-bit strings of weight k are in a very deep sense the same. They have the same number of elements, namely this number b and k, and importantly, they obey the same relationships with each other, especially the recurrence relation that we built up in the last video. There are really just two different viewpoints or expressions of the same data structure, and we can represent one with the other. So in the next and final video, we're going to look one more time at this number b and k and see what it's really all about.